Hello. For those of you who don't know me, I'm Catherine Onafreighted. I completed my senior thesis with Dr. Warren Allman at the Paleontological Research Institute, and I investigated the use of continuous characters in Turritella phylogenies of Panama. Just a little bit of background. Turritella are a genus of snail found all over the world in all sorts of time periods, from the Cretaceous to the recent. And what's difficult about them is that they all look very similar to one another. So there aren't that many traditional characters to create phylogenies with. So we thought it might be useful to try to add continuous characters to the whole character set of Turritella. And this has been investigated previously by Ursula Smith, a previous doctoral candidate here. And she looked at snails in New Zealand. I tried to follow her methods as closely as possible so that our results could be compared. So as I said before, my specimens are from Panama. I have, right now, I'm looking at 10 living and 5 fossil taxa. And I used the largest specimens that I had available to me, ones with the final whorl intact, so that I could use it to generate a character. Also, I needed to use specimens which had protocons available, and not all of them did, but I got a couple. So the traditional characters that I looked at were the basal sinus, which is at the bottom of the shell when you look at it from the bottom, and the lateral sinus, which is on the side of the shell here. I don't know if you can see it quite clearly, but there is an inflection point of the lateral sinus, as well as an apex, which is where the inflection point occurs, and then how deep the inflection point is. I also used the apical and pleural angles of the apex of the shell, as well as a little bit of protocon data from the very tip of the shell. Now that data is not available for all specimens because it's often broken. My next task was to find continuous characters. So I analyzed the whorl profile, since that should be species specific. So the first step was to get a very clear photo focusing on the edge of the shell and labeling where the whorls are. As you can see, the whorls are not very apparent, so having these labels here in another color helps with the subsequent steps. The next step was to read it into R. So R reads it and uses its own color schematic. And then next you analyze the color schematic to find the lowest frequency, and by taking that lowest frequency, you can convert the photo into black and white. So now I know you can see a little bit of pixels here, and that has to do with the cutoff point. So the cutoff point can be adjusted to either take in more of the background or less of the background, but the main thing that I was looking for was the side of the shell. So I wanted to make sure that it was focused on the side and not too pixely. The next step is to define the endpoints of my line, as well as each whorl, which is why I labeled them with boxes, because once it's in black and white, you often can't see where the whorl definitions are. R then traced each step and took the endpoints and whorl points into account, and so those are plotted on the line. And then R generates an outline. Now this outline is not just a line, but a series of points. So it has 200 points with 50 equally spaced points between each whorl. And this is the line which we generate eigenshaped axes with. So I used R to eigenshape analyze each outline, each whorl profile for those 5 whorls, as well as each individual whorl. So where those definitions are, that's where you can either use each individual world or all 5 at once. And I was looking at all 5 at once. So each axis that is generated by eigenshape analysis essentially becomes a new character. Now, you could end up with hundreds of characters, but since they don't vary that much, they generate a lot of noise. So I set the cutoff for this data set at 25 eigenaxes, and so this essentially creates 25 new characters, in addition to the 7 or so traditional characters that I had. So then I use a program, TNT, to create phylogenies from both the traditional and continuous character datasets, as well as combine them. Now, in order to keep aligned with what Dr. Smith did, I set the random seed at 0, used the Wagner trees, subpruning and regrafting, and I outgrouped Turritella since that is actually not from Panama. So I could set that as an outgroup for my data set. Now, first I looked at the traditional data set, the traditional characters, those 7 that I talked about previously, to generate a series of trees. And the best score I had was 22. These are with the fossil taxa, so all 15 taxa. And 53 trees were retained. Maybe some of them are correct. Next, I did a consensus tree. So this is again using the traditional character set with the fossil and living taxa. Now this tree, Turritella is my outgroup. Bacillum fell out 100% of the time. So did Exolita. But here we have some polytomy. So even though in the trees that were all generated, those 53, all became dichotomous nodes, in actuality it's quite unresolved in this tree. Although Mataricana leucostoma seem to fall out quite a bit of the time, and so do Bifasciata and Acropora. So that's one consensus tree. The next, I took only the living taxa. And my best score is 15. 1 tree was retained. This was it. So everything is resolved in this tree using only the living taxa and the traditional characters. So once I added the fossil taxa in the previous tree, generated noise and created unresolved nodes. But that's okay. Next, I needed to analyze the continuous data set. So I did the eigenshape analysis data with the fossils, so all 15 taxa, and that generated about 8 trees, all totally resolved. So again, I took a consensus tree of that data, and Turritella, my outgroup, but this time rubescens fell out. Now, I don't really know why that is, but it's okay, because this is using a new set of characters that have not been looked at for these particular specimens. And so, again, we have this unresolved, non-dichotomous part of the tree here. It seems likely that they're all related to each other, which is good, but we just don't know how they fall out. My next data set was to just use the living specimens, so take out the fossils. Now, 1 tree was retained, and all of the nodes were resolved. This time, Turritella and Bacillum fell out by themselves, just like in the previous trees with the traditional character data. And so that's really good. They agree somewhat. But again, once the fossils were added, it generated a lot of noise. Next, I combined the traditional with the continuous characters. And about 6 trees were retained. I had a best score of about 48. Everything's resolved, but again, we don't know which is correct. So I create another consensus tree. This time, Turritella and Bacillum fall out. So when the continuous character set and the traditional character set are combined for all of the taxa, Turritella and Bacillum fall out by themselves, just like it did when they were separately, but not with the fossil taxa. So now data sets are together and fossil taxa is added, bacillum falls out again, and the rest is a little bit unresolved. But Madaracana and Leucostoma look pretty good about being related as far as the combined data sets go. Next, I added a weighting scheme. So previously in the combined trees, my characters were unweighted. So in aligning with Ursula Smith's unpublished PhD dissertation, I added a weighting scheme. So I weighted the traditional characters by 2 and the eigenshape analysis continuous characters by 1. And so that generated a couple of trees again. And so I created a consensus tree. And now, even with the weighting scheme, Turriber and Bacillum fall out again, and the rest becomes unresolved. But again, Madaracana and Leucostoma fall out. So, which is correct? My conclusion is that I trust the weighting scheme of upweighting the traditional characters because just adding a lot of continuous characters generates a lot of characters, but also a lot of noise. And so since the world profiles and eigenaxes do not vary that much, it's better to use the discrete characters as weighted unequally as compared to the continuous characters. So in the future, molecular data on the living taxa could be used, which is why on some of the trees I only looked at living taxa and did not add fossil taxa. You could also add a map. Since these are all from Panama, you could map these out onto geography for Atlantic and Caribbean sides of Panama. You could also add a time scale. So using the fossils, mapping the molecular data onto it, you could potentially add a time scale to this data set and see when things occurred. And maybe then you could resolve some of the undichotomous nodes. So again, I used 2 sets of data, living and fossil, 10 living, 5 fossil. I used traditional characters that have previously been used in other studies, and also continuous characters, which have also been used looking at other specimens. I took these data sets separately, combined, and weighted, and some things were uninformative, but more work can always be done, more funding is needed, and once you have more data, maybe molecular, geographical, timescale data, you could resolve some of the things that seemed uninformative as of now. In conclusion, I'd like to thank Dr. Warren Allman and the PRI for giving me this opportunity to complete a senior thesis, as well as providing specimens, and also the University of Florida's Museum of Natural History for providing specimens. EAS department, they're great. I wouldn't have spent my years at Cornell anywhere else. Also Kevin Nixon and John Hendricks for helping me out with TNT, analyzing the shells, etc. And also Cornell University's Turritella Research Group, Stephanie Sang, Dana Friend, and Brendan Anderson. Thanks, guys.